This. Hello? 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 Good morning. Welcome back to the last parallel session slot of the conference. I'm very happy to see so full room after yesterday's gala dinner. We were a bit afraid that there will be fewer people, but thanks very much for coming. I think this will be very interesting session. This is the last session of the support infrastructure track. We've had this track all through the week for all parallel sessions. This has been the longest track, and this is the concluding session, which will look at the performance management and some monitoring and resource management issues. We have 3 speakers. They all are network engineers, but I think there are more things in common. You will see from their presentations. Let me introduce the first speaker. Simon Leinen is from Switch. He is a team leader and network engineer, and he will talk about performance enhancement response team and issues related to that. So, here is your presentation. Welcome.
Thanks, Baiba, and thank you all for coming. Is this thing on? I'm not very experienced with these mics. I hope you can all understand me. So I guess most of you have heard about the PERT. Maybe can we have a show of hands of who in this room thinks they know what the PERT is? Okay. So, but there still is a few people. I hope I can explain it to those who are not so familiar with the concept. But maybe some of you are asking yourselves what the heck is EduPERT? So I'll come to that also. So moving right along. The PERT is one of the approaches to a problem that has been identified around maybe 1999, 2000, when there was a big jump in capacity when the new Internet 2 or Abilene network was built and the Geo network was built in Europe. For the first time, there was plenty of access capacity in the backbone. Whereas before, the usual situation would be that long distance network paths would always be congested. So the research community got large amount of funding and built these wonderful fast backbones so that they could declare that now all the backbones are gigabit Ethernet, or not Ethernet at the time, but gigabit speed. But the problem is that most users didn't notice a commensurate performance increase for what they were doing. And this is sometimes called the end-to-end performance problem. The relation between the end-to-end performance, that is what people see in their daily productive work as researchers, for example, does not hold up well to the performance numbers that we advertise for our networks. So the basic question is, how can we help these users leverage the infrastructure that we put so much effort and resources in building to achieve maybe maximum performance or at least the performance that they need to advance their goals as scientists or educators or whatever. So in the early days of the PERT, the focus was really on getting end-to-end performance numbers that somehow had gigabits per second in them. But in my progressing through this work in network performance, I don't think we should be so focused on gigabits per second, and we should really ask ourselves more what the researchers really need and to do interesting works. And the higher layer objectives, the higher level objectives for research networks, why would we even want our customers to use our networks to their capacity? Because that is a reasonable question to ask. Maybe we will create some problems because of that. Well, one reason is that if they don't see that they can use the capacity that they subscribe to, they will never have an incentive to upgrade. And also it allows us to differentiate our offers from commodity internet or commodity networking offers they can get on the market. So one thing that was sort of crystallizes the end-to-end performance problem is what is called the wizard gap. That is like the differential between this nominal speed of backbones that I mentioned and the speed that people perceive when they look at, for example, a download progress bar that says, so you're downloading this file at something kilobytes per second or so. So they never see gigabits per second. Or other applications. And it's perceived that this gap between nominal performance and end-to-end performance is actually increasing. One reason is that in former times the bottleneck was really the speed of the backbones, and now that is no longer the case. Why is this called wizard gap? Well, there are some people which we call wizards who are able to achieve like gigabit transfers on these networks, but it takes a lot of effort and hard work. And we want to help more people to use the benefits of the fast networks. So why is end-to-end performance a hard problem? First of all, the typical networked application in the research networking space where people collaborate over different countries, as the case in Europe. First of all, most networking applications traverse many layers of system components, like the application program that people are using, which are often custom programs written by scientists, and sometimes commodity programs that have not been designed for high-performance applications. There are operating systems and server computer resources, which are in themselves a very complex system with a memory hierarchy with many levels of caching and fast memory and slow storage and buses and network adapters with different capabilities. So just this technical system is very complex, and not many people understand it through these layers. Then there's the multiple administrative domain issue, because usually you traverse some local infrastructure, usually a campus LAN, where the campus LANs have grown to become very complex with virtual LANs and complex edge devices that control traffic and control access, like firewalls or rate shapers. And then we have the national backbones, then we have international backbones such as GEO or Internet 2. And all of these networks, of course, have their support people. And when end users, like in two different countries, two different universities, observe a performance problem, it has been often hard for them to get a support team to really make it their problem. Normally, the traditional organization of support is that so the X NOC, like the switch NOC, is responsible for the switch part of the network, and so the typical reaction to a performance problem that somehow traverses switch is, well, I as switch NOC should try to prove to the user that it's not our part of the network that's at fault. And that can be useful because I may see that there is indeed a fault in my network and I have to fix it. But in some cases, the problem is more complex like that, and you don't have a clear-cut single point that you can point to that is the culprit, the root cause. Sometimes you have multiple, or often you have multiple dimensions where you can address a performance problem, and you really have to look at the problem as a whole. So the buzzword for this problem is finger pointing loops, which is the situation where you have a customer with you have researchers, users with a performance problem, and they are pointed from support organization to support organization, with each one saying, so no, my system, I can assure you my system is okay, all the lights are green, all the links are up, we don't see any errors, so please look somewhere else. Maybe it's your stupid program, or it may be these other networks in another country where you don't have direct access to the people. And that is the situation that we should address. So there are various approaches that have been proposed since about 2000, I think, to address these end-to-end performance problems, and PERT is just one of them. There are others which are equally useful and have led to great progress, such as the work on making operating systems, especially the TCP implementation in operating systems, more adaptive to different network situations. As recently as 3 or 4 years ago, the typical operating system, even like for high-performance computers, workstations, or servers, would come optimized so that it could work on a fast local network well, or it could work well on a slow, over slow internet paths, but not over fast internet paths, such as the ones that we are providing our users, the so-called elephants or long fat networks. So these are the paths that have high capacity but long delay because of distance and light speed issues. TCP has traditionally performed badly in these situations, but over the past years, the operating system vendors, including for mass systems like Microsoft or Apple, they have addressed this nicely. So today people will get a much better out-of-the-box performance for TCP. There are other approaches include self-diagnosis tools such as the NDT tester that some of you may have used to look at bandwidth restrictions for your TCP application. Should also mention, performance monitoring approaches such as PerfSonar or the passive monitoring tools that Sven will probably talk to you in less than an hour. Of course, there are efforts at user education, and the PERT also works in that area through the PERT knowledge base. But what the PERT is really a human infrastructure for assisting users with performance problems. So again, that's a double quote missing. Okay. So to answer the question of what the PERT is, it is supposed to be like the CERT. The structure that the CERT has provided for security problems, we want to be this for performance problems. So as part of the functions that the PERT should provide is we should try to really understand users' performance requirements, which is often a very significant and hard part of addressing the problem. Own performance issues that have no natural home otherwise because they span multiple administrative domains. Apply cross-layer thinking, which does not mean that PERTs by themselves have to understand all these complex network systems problems that cause bad performance, but at least we have to have a general understanding of the interactions between the layers. The PERTs should suggest steps to diagnose problems or also help in doing so by getting access to measurements within the network or helping users take packet traces and help them analyze them, which is sometimes difficult. There's also a coordination function similar to what CERTs do. In communication between PERT teams is very important so that you can collaborate with people across networking domains. And then towards reaching the goal of improving people's performance, an important part is to identify the bottlenecks and have a pragmatic approach of what can be fixed. So just telling the user, well, this is the bottleneck, you fix it and the problem will be better. You have to think about the implications that has and how realistic it is for a user to fix something. And this will differ from situation to situation. Some people can afford network upgrades, other people can afford to rewrite or restructure their applications. This also demands a lot of thinking. So historically, I think the PERT concept came up in discussions between Internet 2 people and Géant people, or maybe it wasn't Géant, called Géant at the time. In 2001, within Géant, we had a pilot where some of the people in the room and from NRENs collaborated and proposed structures for working. The phase where the PERT had the most visible emanation or manifestation was during Géant 2, not quite till the end of Géant 2, where we had a Géant PERT that consisted of volunteers or Géant participants from various countries who took turns weekly or bi-weekly to staff the PERT for the entire Géant community. Then towards the end of the Géant 2 project, we decided that we decided to move to a different structure, and that is called the EduPERT, or the federated PERT. So what is the EduPERT? As I said, towards the end of Géant 2, we decided to decentralize the centralized PERT that we had at that time for some reasons. I can go into them if people are interested. So the idea was to have PERT teams distributed. They would be certainly in hopefully many NRENs, probably not all, certainly not all from the start. But campuses, campus NOCs could also provide a PERT function if they thought that useful. And also large projects in the spirit of DISA or LHC grid could be expected to have such an explicit PERT function. So the idea is to have the PERT teams close to the user, and of course these distributed teams cannot entirely work in isolation. That's the nature of the end-to-end performance problem. So there's some support infrastructure that is shared or provided centrally. First of all, there's a common policy that should govern the work of these PERTs. That is the policy for a federated PERT, which has been delivered towards the end of Géant 2. It's this document. There is currently a website under edupert.géant.net that is like the public entry point. It doesn't have that much information, but it does contain a registry of the PERTs that have bothered to be registered. So that is one of the central functions. If you have a PERT yourself or you know somebody who has and it's not listed on this page, then ask them to submit a registration. There's an email address for that. There's actually another level of registration which we call accreditation. That has never been tried, but we're starting that process now, which allows PERTs to have like a higher status if they commit to certain additional duties and performance thresholds in terms of mostly response time, and submit a little more information about themselves. For the past 2 years, we had PERT training workshops, which included both methodological and organizational, but also a lot of technical information for people who want to provide this PERT service to their customers. And that has been a success, I think I could say. So I hope that will continue. I don't know how or whether it can be funded under GN3. We had some funding in GN2. And there should be meetings for information exchange, informal information exchange between the PERTs, although it's not clear to me now what would be the best place to have such meetings. In GN2, we had some PERT get-togethers at the technical workshops. I'm not sure whether this can work in GN3 or whether there are other venues suitable for this. So if you have any ideas on this, I would be grateful. Maybe Terena or TNC would have been a good opportunity to meet between PERTs, but we certainly missed it for this time. There's also the PERT knowledge base that I briefly talked about, which collects a bunch of performance-related information, and it's actually a wiki. So in principle, anybody who has something interesting to contribute could do that very easily. In practice, it isn't evolving as quickly as we might hope. There's also some central reporting which have been performed by Dante in GN2, which consists of Dante asking every known PERT to submit monthly numbers of how many cases they opened last month, how many cases they closed, and how many cases were still open by the end of the month. And this is included in the GEO monthly service reports, which you all read from start to end, I'm sure. But what's missing is what these cases are about. So as an illustration of the kind of cases that the PERT has worked on in the past, I have two small examples. Some people might know this. This one. This is close to the typical case we were addressing in GN2, in the GN2 PERT, which were pretty often stated in terms of, well, I need single stream TCP performance and I only get this much, but I thought I could get this much. So in this case, the users reached 150 megabits per second between 2 points between the US and Germany, which is not bad for starters, but they thought they should get like more in the region of a gigabit per second. So initially we thought, well, this is the typical problem that people don't know how to tune their TCP stacks. But then later it turned out that it was actually a network problem that had been in the Géant backbone for many months probably, and they were just the first to notice this problem because it manifested itself as very low, near constant packet loss on a very important and busy link. And 99.9% of the Géant users never noticed this. But if you try to do single stream TCP performance, then performance breaks down. So this actually fixed a bug in Géant. So this is why we can sell this as a success story. Of course, after that problem was fixed, this simply uncovered bottlenecks somewhere else in the system, namely LAN switches in one of the participating sites that had insufficient buffering. So this is also a recurring story. You find one bottleneck, and then it turns out there are new bottlenecks that also have to be addressed. So again, lessons learned. Low loss is unnoticeable for most people, but there are situations where it can have dramatic effects. And the work that had to be performed to prove that the network was indeed losing packets along the path was very significant. This is something that networks are not good at, allowing you to prove that they're losing packets. So within the switch, we have been offering, or officially offering a PERT service for a couple of years. So it has become known to our constituency. We are we've always worked on different kinds of problems, sometimes very mundane, like access to this web server is slow or so. We would treat them as PERT problems. But lately, we found that a new development that we didn't quite anticipate, people come to contact us in early stages of when they want to do something they hadn't done before that they think is interesting, and also for us it's very interesting to hear more about what cool things researchers really are doing with the network. So they contact us before they actually try doing it, and that is I think that the PERT can also provide a useful service to these users by reality checking their expectations or telling them, yeah, this is a reasonable thing, you can do this on our network, no problem, it should just work, or yeah, you have to look at this and this problem, or in some cases we can say, yeah, this is possible, but it will be better if you upgraded your 1 gigabit campus connection to 10 gigabit, and then hope that you can get a sale through this recommendation. And also sometimes you find that the users really need outside assistance. For example, we have this case of people who try to organize a conference in 2 locations in Switzerland and Japan, and they want to have like a live link so that people would have the experience of a single conference. And we found that they should really look at professional video equipment and setup. So we located people who could help there. And then there's the problem of following up, because typically in these cases, you might never hear from the customer after the first exchange. And normally this is a good thing because it means that they somehow solved their problem. But it's still useful to ask back from time to time. So for EduPERT, there are some challenges which have to do with moving from the centralized model to the federated model. The main problem is can we sustain the momentum of the PERT without having a strong core? The strong core in JN2 was were the teams that handed over the JN-wide PERT duty every week and had to tell each other what they were working on. And there was a ticket system that contained all the information about all the cases, and now we no longer have that. So I think we have to work on this some more. The training events, they prove to be useful, and it's a lot of work organizing them, but that is something that I think is worthwhile. As I said, we should also continue to have meetings within the PERT community for information exchange, and I'm open to suggestions on where to have these meetings. Of course, there's also a mailing list, but you may also have this experience. It's hard to make people contribute to mailing lists. The reporting could probably be improved a little by doing more than just counting cases and maybe asking people to contribute at least one-liner descriptions of the cases they're working on or the cases that they have solved. And also the PERT knowledge base, I think it should play a role in recording the collective wisdom of the PERT, including things we learned, and also just the PERT case stories. Otherwise, I think we should work on continuing to expand the scope and getting more NRENs to adopt the PERT idea, and also maybe moving beyond Europe, because it's originally not just European idea. As to technical challenges, I think the coming years have exciting promises for work on difficult performance problems. One is the move to more parallel architectures in computing as a whole, like the multi-core or many-core evolution. In some respects, I think this will make performance problems easier, because I think that the high-performance networking traffic will resemble more the normal internet traffic, and it's more natural to have many connections between many processes than to have a single or a few huge TCP connections between processes. But of course, it also introduces new problems. There may be take-up of large commercial infrastructures such as Amazon clouds, also for high-performance applications. There's virtualization and the whole problem of diagnosing performance issues on virtual machines and maybe virtual networks in the future. VPNs have already shown up in our practical work as a source of performance issues. There's more and more wireless. You're all connected wirelessly here because there are wireless buses and so on with their own performance problems. And lately we also had worked with people who have data collection requirements, who have sensors like seismometers in the field distributed in the country, and they send continuous streams of data over funny kinds of networks. So I think these will be the frontiers for the future. So briefly, a few arguments for managers why you should consider developing a PERT function in your organizations. It's really something that for networking people, it's very rare to have these what economists sometimes call customer moments of truth, where somebody really notices that you're there. Normally in networking, those are always negative. So then you notice the network only when there are problems. So we hope that the PERT will give positive customer experiences where people really realize that you're doing a useful job. It also has some organizational advantages by providing interesting work to experienced personnel that you don't want to leave the organization. But of course, it doesn't work for all kinds of organization that I accept. If you're an engineer, consider doing PERT work. It's a great way to help some people and help people who want to do exciting things and learn about these new things. It's also technically very challenging. You will learn new skills, not just in networking, but also in dealing with people's issues in a constructive way that are generally useful. And most of all, it's just a lot of fun and a great community. So I hope you'll join this activity if you're not already in it. Thanks a lot for your attention. I hope we have some time to take questions, or do you have?
Are there any questions?
You showed one problem where on the link it turned out that you had two problems on one investigation. So this gives me the feeling that actually there are many more problems out there than sub-percent chance. I mean, to have two problems on one link is like, two bombs on one airplane flight. The probability of that should be squared. So what I want to say is, so if you have two problems on one link, that means that almost every link should have principally a problem.
Yeah, probably every link has a problem, but usually those don't have any effects. I don't know, it's also a little...
If you have two problems, you multiply the probabilities.
Yeah, I have trouble with this approach of having problems or not. I mean, these users had high expectations and high requirements, and the system didn't fulfill the requirements for them. But that doesn't mean that it was not, that the path had problems for anybody else. So I don't think networks are usually either broken or unbroken. We engineer them for a common use case, and then there are people who have a different use case, and we want to cater for these people as well. So this is just one approach of allowing deviations from the general use case, and I think we owe that to our customers.
In one of your faults, you said it can be very hard to locate packet loss in a network or a problem, whatever. Who pays for it if there is a problem? And we ask you. For example, if there is, you know, the DISA network is a problem.
Yeah.
A to B is a very good throughput. A to C, it's bad.
Mm-hmm.
And A to C may be Géant, 2 NRANs, 2 local networks. So who investigates and who pays at the end the cost for this investment?
Yeah, this is a good question. For this long investigation, which really took weeks of work, this was paid for from Géant project funds because it was considered development. So if you think about moving to a sustainable model where you have people paid out of normal business, I don't know. It's in Switch we have not yet considered unbundling it and charging for it extra. It is part of the excellent service quality that we strive to provide, and maybe the business case for us for doing this is if people learn that they can expect us to help them in the case of these different problems, and we go to great lengths to do this, then they will see this as an argument to pay more, maybe more for NRAN connectivity than they would for commercial connectivity. But yeah, I'm not sure the cost can be recovered through consulting fees or something. Maybe it could, I don't know. It will be interesting to know from you how much would you be willing to pay, because you're already paying presumably a lot for infrastructure, computing infrastructure, and for networking. Maybe you get the network for free, I don't know. Maybe you would also be willing to pay for people who fix the problems, either transparently as part of the network subscription or through some kind of consulting fee.
Okay, thank you very much, Simon. Yes, indeed. Okay. Okay, hello. This brings us to our second presentation, which will be given by Anastasios Zafiropoulos from GRNet. He is a network engineer as well, and he's going to talk about using peer-to-peer technologies for network monitoring and resource management. So, this is the presentation, and the floor is yours.
Thank you very much. Hi to all. I'm going to speak about how we can use peer-to-peer techniques in order to facilitate performance monitoring and the resource management in autonomic networks. And this work is done by my colleague Thanasis Liakopoulos and me from GRNet in the framework of the FIPSAN's FP7 project. So just an outline of the presentation, a few words about peer-to-peer network characteristics and autonomic network characteristics. What is the FIPSAN's project and the proposed generic autonomic network architecture in this project, and then how we can apply peer-to-peer techniques in autonomic networks. So regarding the problem, as you all know, IP networks are becoming more complex and larger, and it's difficult to manage and monitor them. We refer especially to heterogeneous and dynamic environments where we have a lot of changes in the network topology, nodes join and leave the network. It's very crucial to have efficient resource discovery and management, and due to a lot of changes, it's not efficient to put in a standard monitoring scheme. So, in order to address this issue, we apply autonomic principles in data network management, and we do so because in an autonomic environment, the network can detect, diagnose, and repair failures. It's able to adapt its behavior according to the network conditions, and also to follow policies for improving its performance and the provided functionalities. So we refer to wireless networks, and we have seen that there are a lot of similarities between ad hoc networks and peer-to-peer networks. So it's worth to try to see which peer-to-peer techniques we can exploit in order to monitor and manage autonomic ad hoc networks. So, in a peer-to-peer network, the basic operations that are implemented are lookup queries for searching information, routing, how peers join and leave the network, and also how the data are stored and are accessed by all the peer nodes. There are also several performance metrics defined for the efficiency of a peer-to-peer network, such as the efficiency of the data lookups and the data inserts, fault tolerance in case we have broken links or some nodes leave the network, load awareness regards how peer nodes know about the network conditions and the connectivity with other nodes, proximity awareness for the peer nodes to be aware of their neighbors, scalability issues, and also how content is distributed, and of course, network routing performance. Now, in an autonomic network, we have also several challenges that are similar with peer-to-peer, such as dynamic topology, where links are established and torn down according to the network conditions. There are several nodes that may play specific roles, and in case of changes in the network, these roles have to be reassigned. And also, we have a lot of complexity because in most cases, there is lack of centralized control. So, which characteristics of peer-to-peer networks can be exploited? Ad hoc deployment, where we have dynamic assignment of tasks and roles in several peers. We have to select nodes that don't consist sync points of failure. Peer nodes share their available resources, and also super peers are defined in a lot of cases in order to play specific roles. Also, peer-to-peer networks provide several guarantees about performance issues that can be also exploited. And in peer-to-peer networks, there are also several challenges about security, improvement in the robustness, and advanced monitoring and management. Now, coming to the EFIPSANS project, EFIPSANS stands for exposing the features in IPv6 protocols that can be exploited or extended for purposes of designing or building autonomic networks and services. So we are trying to describe several autonomic functionalities, and an autonomic network architecture is proposed. It's called GANA, in order to describe this kind of functionalities. And recently, an ETSI industry specification group called DAFI for the autonomic network engineering for the self-managing future internet has been established. Now, a few words about the proposed architecture. It's called GANA, and GANA separates specification issues for autonomic behaviors from implementation issues. We have reviewed previous proposed architectures, and the difference in GANA is that, first of all, decisions can be taken by individual nodes without involvement of a centralized entity, and also in GANA we can also design autonomic behaviors that regard all the network in network level and not just in node level. So there are 4 planes defined. Decision plane for making decisions regarding the network or the node. Dissemination plane that describes mechanisms and protocols for dissemination of information. Discovery plane for discovering services in the network or discovering new nodes and topology issues. And also the data plane that implements protocols and mechanisms that handle individual packets based on the decision plane. So the basic concept in this architecture is also in its autonomic architecture is a decision element that either in a node, either in a network level is able to manage some managed entities and to receive information from the managed entities or from other information suppliers and to take some decisions. So some control loops are established that facilitate the decision element to manage the managed entities. And there can be several kinds of relationships, either hierarchical, where a low level DD is managed by an upper level decision element, peering, or sibling, where some managed entities are managed by the same upper level decision element. So you can see also in the figure, we can have decision elements in node level, decision elements in, that implement specific functionalities such as routing, mobility, QoS, etc. And also decision elements that implement some protocols. Also, there are peer relationships between the decision elements and sibling in case where two functionalities are managed by a decision element in the node level. So these are the levels that a decision element can be, either in a network level for managing and determining network behaviors, node level for managing the node, functions in order to manage particular networking functionalities, and also protocol and mechanisms in the protocol level. So a generic figure about the control loop the control loops that are established, where we have decision elements that manage entities and can or trigger or execute a behavior or apply a policy, and then information is received from the managed entities to the decision elements in order to take decisions and to implement the control loops. So we have described a monitoring decision element which is responsible for describing all the monitoring functionalities in the network, in an autonomic network. So in each node, we consider that we have a monitoring decision element that is able to communicate with other monitoring decision elements and so take decisions about monitoring. So in this decision element is responsible for traffic monitoring coordination, topology and resource discovery, monitoring the state of the node, and also we are working on context awareness on how to exploit ontologies and information models in order to recognize fault and conflicts in the network, or also to provide services, registrations, accounting, etc. So the monitoring decision element manages several monitoring managed entities for implementing monitoring mechanisms, and also it can receive goals and policies from a main node decision element, which is a decision element that manages all the node. That's all for the monitoring team. Now, how we can exploit peer-to-peer techniques in such kinds of networks? As I said, we are referring to dynamic topologies, where ad hoc networks, where we have joins that nodes that joins and leave the network. So we are considering that autonomic nodes create an overlay network, and all the functionalities are provided in this overlay network. But how can data be distributed among the nodes? Several techniques can be applied. For example, hash functions can be applied for generating keys. For example, these keys can be 64 bits as the interface ID of a typical IPv6 address. Then each autonomic node can calculate its identification key according to the hash function that we are using. And then we can assign the keys to several nodes, that by assigning in each node some keys, it is responsible for the content that is coming from these keys. So a node may be responsible for the content of several other nodes. Also, with the same way, performance monitoring data related, for example, for a link from node A to node B can be stored in the node responsible for the key generated by node alpha with the tag of the key of the node B. So to know between a path where is stored information that regards this link. In the same way, we can retrieve monitoring data by applying the reverse functions. And it's very important to study and to see which peer-to-peer protocol is suitable for each topology. because there are a lot of protocols proposed according to the environments. Now, regarding resource management, as you know, in order to provide resource management and performance guarantee in a network, you have to know information according to the flows that are in the network. For example, in a DSEV network, it's necessary to distinguish the ends from the core nodes. And the intelligence of the network is usually on the edges. So we're suggesting that in an ad hoc environment, the nodes that are creating the traffic to be the end nodes of an overlay network. And this overlay network will be responsible for providing resource management. So we have an ad hoc network, we have several edge nodes that are generating traffic, and this creates the overlay network. So the establishment of this network can help us in order to manage policies that the edge nodes apply to other nodes, to measure the total traffic injecting in the network, and also to establish peer-to-peer measurements among all the network. In the same way as we described earlier, we can apply peer-to-peer techniques for managing specific links inside the network. So, in this presentation, we have described several functionalities of peer-to-peer networks that can be applied in autonomic networks. It is important to refer that we are working according to GAN architecture, so we are trying to map all the mechanisms in this architecture, and we have described how storage and retrieval of monitoring data can be applied. So in our future work, we are going to enhance the proposed monitoring framework in order to integrate peer-to-peer techniques. We are going to identify the decision elements that are responsible for implementing this monitoring and management. Also, how we can support multidimensional queries or other distributed databases, and also make some simulations in order to validate all this try. So that's all from me. Thank you for your attention. If you have any questions.
Questions, comments? Okay, thank you very much.
Thank you.
So thanks for the quick presentation. We are on schedule back. Now it's time for the last presentation of this session, and this will be given by Sven Ubik from CESNET. Sven also is a network engineer, and he has very long working experience with passive network monitoring. And his presentation is also about passive network monitoring. Here it is. Yes. So, floor is yours.
Good morning. My name is Sven Ubik. I am from CESNET, and I would like to present you some of our experience with deploying passive monitoring in GEAN2 network. Let me introduce what passive monitoring is. Most computer network monitoring methods can be classified into 3 areas. In active monitoring, we send test packets into the network and observe what happens with these test packets. In passive monitoring, we do not send anything in the network. Instead, we capture and analyze the real traffic which is already there. And in network infrastructure monitoring, we collect information from network equipment. An example of this type of monitoring is SNMP protocol. Each of these monitoring approaches has its advantages and is suitable for different network characteristics. For instance, active monitoring is the easiest way to measure network delay, and advantage of network infrastructure monitoring is that data sources are readily available because these are routers and switches installed in the network. So we believe that a comprehensive network monitoring system should be based on balanced combination of all three approaches. As for passive monitoring, it has some interesting properties. First, it is non-intrusive because we do not send anything in the network. And second, and more importantly, it can provide information about real network traffic which can be obtained from other means, that is from test packets or from network infrastructure. Examples of such characteristics are the load dynamics in different time scales, including short load peaks, what protocols and applications are being used in the network and what are trends in their usage. Or we can use it to detect various kinds of anomalies in network traffic that may be signs of network attacks. Or, for instance, we can use passive monitoring to monitor real packet loss of the user traffic, which is difficult to measure actively, as I will show later. On the other hand, passive monitoring has also some difficulties. The most important one is that it is compute intensive, because we need to process not just a few test packets, but all traffic which is in the network. We did a pilot deployment of passive monitoring in the GN2 network. There are 4 partners, ACAT, CESNET, Pioneer and Switch. And we deployed monitoring stations on border links between the GN2 network and national research networks. 3 of these border links were 10 gigabit, 1 was 1 gigabit. The central user interface has a very simple address. It's perfmon.gn2.net. There is username and password, and because I would like you to look at my slides instead of the web, I will show you the password later. So what hardware is needed to deploy passive monitoring? You need 3 things: something to tap the monitored line, a packet capture card, and a PC. As for tapping the monitored line, you can use an optical splitter or a router mirroring port. Router mirroring ports are generally scarce. There can be only 2 of them even on high-speed routers, and their performance is limited. Therefore, they are useful only in cases when you want to monitor more links leading to the same router at the same time, and you want to collect traffic from all those links into one mirroring port to use one packet capture card. In other cases, it's better to use an optical splitter. If you want to monitor a limited volume of traffic up to approximately 300 megabits per second, you can use a regular Ethernet card to capture packets. But if you want to monitor more traffic, you need a specialized monitoring card. It looks like an Ethernet card, but has better performance. It differs in 2 properties from the Ethernet card. The first thing is that the monitoring card can copy all traffic up to the full line rate, that is, for instance, 10 gigabit per second, at all packet sizes from the network to the PC memory with 0 CPU load, so that all CPU power remains available for packet processing. And the second difference is that the monitoring card usually provides some acceleration, such as packet filtering or classification. As for the PC, the faster is better. And in short, we can say that the speed of main memory is the most important factor. It proved to us that with the current technology, multi-lane, fully buffered DIMMs are probably the way to go for using PC for passive monitoring. So what software is deployed on this hardware? There are three types of software. First, there is a Linux operating system plus drivers of packet capture cards. We use these as they were without modifications. Then we use middleware to support applications, which is called DMAPI. This stands for Distributed Monitoring Application Programmable Interface. DMAPI is a set of libraries which were originally developed in Scampi and Lobster projects and which were further adapted in GN2 project. And these libraries provide a higher level of abstraction for programmers of monitoring applications. Programmers can use these libraries to relatively easily create applications that are portable across different packet capture cards. The same application can run without modification over different packet capture cards. And at the same time, if you have one packet capture card, you can run multiple applications concurrently at the same time, sharing these hardware resources. And finally, middleware DMAPI also provides transparent hardware acceleration. If you use a packet capture card that includes some hardware acceleration, it is automatically used by the application. If you use another packet capture card that doesn't provide hardware acceleration, everything is implemented in software and it is transparent to the application. So what applications we deployed? ABW for load dynamics and protocols and applications detection. Packet loss to monitor packet loss in real traffic. Burst to measure traffic burstiness. TBW tools to measure TCP throughput with diagnostic. So this is a hybrid application, active and passive. And finally, perfmon and surfmon are service applications that support reliable operation of the monitoring infrastructure by checking status and resources. Because of the limited time, I decided to say more about the first two applications, which are probably the most interesting. The ABW application is designed to monitor network load in various time scales, including short load peaks, and to show how traffic is distributed into protocols at different layers of the OSI hierarchy. It is currently configured such that it provides two types of graphs. The first graph shows distribution of traffic into layer 3 and layer 4 protocols. And the second type of graph shows distribution of traffic into layer 7 protocols, that is application protocols. The ABW can detect most commonly used application protocols that use dynamically assigned ports. This is done by the TrackFlip library, which is one of the libraries of the DMAPI middleware. These libraries provide so-called monitoring functions for applications, and these libraries are easily replaceable. So, for instance, we may have multiple versions of the TrackFlip library that use different protocols, different algorithms to detect level 7 protocols, and they may use different hardware acceleration means, which is what we plan to do in our future work. The second monitoring application I would like to talk about is packet loss. Let me introduce the problem. In current high-speed, long-distance network circuits, even small packet loss rates, such as 10 to -5, for instance, can seriously affect TCP transfers and applications. So it's good to know if such a packet loss happens in the network. And packet loss is traditionally monitored by active monitoring, by using test packets. The problem is that if we send, say, 100 test packets per second, which is already more than what is usually used, then it would take 1,000 seconds to detect a packet loss rate of 10 to -5, and provided that the packet loss happens evenly. So clearly this doesn't scale for full mesh monitoring between multiple points when we want to detect packet loss quickly and realistically. Moreover, active monitoring can be used to find out what applications and what users were affected by packet loss, and they are particularly bad in detecting loss bursts, which often happen in the network. For those reasons, we decided to create a passive packet loss monitoring application, which is based on surprisingly simple idea. We deployed monitoring stations on border links over network, that is on links between the GEAN2 and NRN networks. And these monitoring stations send records about completed flows to the center station. This is similar to NetFlow, but these records include more information than in standard NetFlow records. They are optimized for space, and they are collected by the central application. If the same flow is reported from multiple monitoring stations, and there is a difference in the number of packets in these reports, then we know that packet loss happened. So the idea is simple, but the implementation includes lots of intricacies, such as we need to make sure that no false packet loss is reported during application startup when we capture flows in the middle. We need to detect direction of flows, and so on. So the result is user interface which provides many tabular statistics and 4 types of graphs. The first graph in the upper left corner shows distribution of expired flows over the time. That is the number of flows per second detected on each monitoring station. The second graph in the upper right corner is provided for each pair of monitoring stations. That is not for one monitoring station, but for pairs of monitoring stations. And it shows time distribution of matched flows for pairs of monitoring stations. That is, flows that were found to flow from one border link to another border link. And using these matched flows, we can compute the packet loss count and packet loss rate, which are presented in the other two graphs. So to summarize our experience the link load on the monitored link in each direction ranges from about 300 megabits per second to almost 10 gigabits per second, depending on the link, on the time of day, and on the time period which you used to calculate average load. And we found that with the applications that we deployed, we can reliably process approximately 5 gigabits of traffic sustainously using one monitoring station with 2 CPU cores. Unfortunately, the monitoring cards that we use can split traffic into a maximum of 2 memory buffers, which can be served by 2 CPU cores. So we can't effectively utilize more than 2 CPU cores. But even if we could, we would probably not have increased this throughput significantly, because it appears that the limiting factor is the speed of the main memory. We have some small number of packets dropped by the monitoring system. It's at the order of 10 to minus 6. We are not sure where these drops happened, because CPUs are not overloaded. It can be the memory problem. As for whether this number of drops packets affects monitoring applications, there are 2 classes of monitoring applications. The first class is of statistical nature, and a small number of dropped packets does not affect its results. For instance, ABW application can still provide very precise results even with the small number of dropped packets. On the other hand, there is a second class of applications which need to process really 100% packets. The example of this class of applications is packet loss. So far, we were lucky. We found that the periods of time when the system dropped some packets were different than the periods of time when matched flows were identified between different monitoring stations. So the monitoring results were not affected. But we are, of course, going to look at this problem in more detail. So you can find username and password on the Geant2 wiki page to log in to the central user interface, and you can access the monitoring applications. And the last slide is about our future plans. First, we plan to look at lightweight methods of application protocol detection to replace the track-flip library, so that it will be more scalable to higher speeds and to newer protocols. Second, we plan to check if the packet loss application can use standard network records. In that case, it will be a network infrastructure monitoring application instead of strictly passive monitoring application. Then we are looking at less expensive options to current 10 gigabit monitoring cards, which are unfortunately very expensive. One option can be our own hardware device, which we have developed, that is called Modular Traffic Processing Platform, which runs at 10 gigabit speed. And finally, we are also working on 40 gigabit monitoring, and we already have our own 40 gigabit device, which can do bit error rate test at full speed of 40 gigabits. And we are also looking for more partners to collaborate and to use our results. Thank you.
So you said that 10 gig monitoring cards are very expensive. Can you give some idea what order of magnitude that would be?
Roughly the cost is 15,000 euro for 10 gigabit card. It's a comparable price for all manufacturers.
Okay, and 1 gig? That's probably much more reasonable.
1 gig, I think that it ranges from 4,000 to 7,000 euro.
Okay, maybe any other comments, questions? Then go to the wiki page, look for the password, and join the thing. Thank you very much, Sven. Thank you very much for attending.